Okay, so let's quickly revisit back what we have learned last week, right? We discussed first half of our topic 1, right? If you still recall that basically there are 5 different key focus. Okay, so let's look at this. All right, so last week we talked about the data itself. Okay, right. Then we move to looking at several commonly used time series model, right? So we kickstart with the first one. Okay, so later we try to briefly go through it so that you can recall back what we have learned, right? Now today our agenda is simple. If possible, I would like to quickly finish up this topic. I do not know whether we can do it or not, but let's give it a try. Okay, so the other remaining key focus for this topic 1 will be we will talk about one of the very crucial assumption on using time series data, which is what we call a stochastic process. Okay, so this is the one of the most crucial assumption. Basically, for this course, there are 2. This will be the first one. Also, I basically want you to pay a little bit attention on this assumption because this concept will keep on reappearing when we discuss along the subsequent topic later on. Okay, right. Then we look at after we look at the assumption, we look at one of the common pattern that we normally seen in using time series data. So as mentioned last week, right, when we use time series data, what makes time series data so unique in the sense that it compared to cross-sectional or panel data, they tend to portray us a very unique features, which is what we call the interdependency of your data point, right? So this period is basically influenced by last period. So data point now and data point the next period, right? They must be ordered in time. We cannot simply change the sequence of the time. So we call this a sequential order. Okay, so because of these unique features, you see that most of the time when you try to visualize the time series data, they show us a very clear trend pattern, and then we try to look at what is this all about. Okay, and lastly is that I want to draw your attention to one of the most significant or most common problem encounter when you're trying to use regression on time series data. Okay, in fact, you see that previous studies in the 70s, in the 60s, right? Those who use time series data by using time series analysis, by using regression analysis, those kind of result might subject to what we call a spurious regression problem. So this is one of the key problem when our assumption doesn't hold. Okay, so previously, many of the empirical research, they tend to ignore this problem, right? Since 90s, in the 80s and the 90s, right? Everyone start to alert about this problem, and basically there is a need for you to trying to pay attention to this problem because before you start to do your regression analysis using time series data. Okay, so basically this will be the key focus, so that I hope that this roadmap, right, will help you to do your revision later on, right? I want you to look at the link between the concept that we learn here. Okay, so that later on when you do your revision, it will not appear like in a very scattered manner, right? So try to focus on these 5 key issues as mentioned previously. When I try to set my test question or final exam question, I will just look at this kind of key focus so that you can grasp what is the emphasis in the class. Okay. All right, so last week we start with talking about time series data. What is that all about? In a very simple manner, time series data is just a data point that arranged in a time sequential manner. Okay, all right, we try to look at different type of time series operator. What do we do, right? How do we process our time series data? We learn some notation, like for example, lead and lag, right? And then we look at how do you look at the growth rate by doing differencing, and then we try to look at the log data and so on and so forth, right? This is nothing new, right? Okay, so and then we look at what's so special about time series data, right? What can we do with that? Okay, so basically we look at 4 different perspectives, right? Whereby the time series data, they are unique in this sense that they offer information to allow us to do some forecasting model, right? To study the volatilities, right, and then trying to examine or investigate the long-run relationship as well as the short-run relationship. These are the things that we have covered. Okay, now looking at this second part, right? So we try to venture into this commonly used time series model. As mentioned previously, what do you mean by model? Model is just a simple description about the real world. So how do we view the real world? Okay, so you have your model, I have my model, everyone have your own model. Our most challenging part is to convince others that our model is a better description of the real world as compared to others. Okay, so we see that in the empirical research, there are many types of model being used. Okay, so for time series data, there are several very commonly used model, right? Basically is ranging for this. So all this kind of model we will learn for this 14 weeks, right? Last week we kickstart with the first one, which is what we call the smoothing procedure. Okay, so the first half for topic 1, we will talk about the first one. This is a very classical way for you to look at time series data. So as mentioned, right? Even though we say it's classical, but with the emerging of big data and stuff like that, you see that this kind of classical method or procedure making a comeback now. So this is why the focus now is back to this kind of classical method. Okay, so the remaining one we will cover in the subsequent topic, for example, univariate model, bivariate model, multivariate model. Okay, so let's look at the next one. So this is the one that we'll be talking about in topic 1. Okay, so now last week we talked about the smoothing procedure. If you still remember, smoothing means what? Smoothing means given a set of data, sometimes from the visual plot, we can't see a very clear pattern. Okay, because sometimes, particularly when you have a very high frequency data, okay, the data show a lot of noise, right? Noise means chaos or fluctuations. Okay, so sometimes the signal is not that clear, right? What do you mean by signal? Signal means the direction of the data. So where the data will go, okay, whether you have an upward trending pattern or downward trending pattern going up or going down. So because when you want to look at your forecasting, okay, one crucial question probably your boss or your customer might ask you, hey, what do we expect in futures, right? Is it going up or going down? So when you ask this kind of question from statistical point of view, basically is that people are asking about these things, the signal, which is the direction. Okay, so how do we see this graph, for example? Is it going up and down, or is it horizontally, vertically, and stuff like that? So going up or going down. So sometimes, or most of the time, we can see that the visual plot is not so clear cut. So the signal is not clear in our language, right? The signal. Right, signal means the direction is not clear. So why the signal is not clear? Because there are lots of noise. Noise here means what? Variabilities. Okay, fluctuations. Okay, So signal here means what? Signal here means the drift lah. Drift is going up or going down. Okay, so because of the noise, we can't see the signal clearly. So what do we need to do is that for the smoothing procedure, our ultimate goal is to reduce this noise in the data. Okay, so last week we looked at one very simple and commonly used procedure in removing the noise by smoothing the time series data. So how do we do that? Okay, so last week, as mentioned, smoothing try to help us to better see the pattern, right? So we look at you trying to smooth out the irregular roughness. Roughness again here means the chaos or the noise. Okay, so right. This is the example that we go through. So let's say if you have a data set, you can't see a very clear pattern because of this fluctuation over the time. So what we can do is that we can trying to get the smoothing average, the moving average, tree moving average, for example. Okay, you see that this is the blue dot line here indicate that this is the moving average tree period. Okay, so how do you do that? Basically, you trying to total up 855 plus 847 plus 1000, you divide by 3 for the first observation, and then you see 847, 1000, and 635, and then this one you get the 3-month average, this one you get the 3-month average, this one you get the 3-month average. You try to rolling the data, and you see a new data point that give you a more smooth edges, trying to smooth down all these sharp edges. So you see that you tend to see the signal more clearly. So this is what you see. Okay, so last week is about the smoothing procedure, right? Idea is very simple. You try to use the moving average to trying to reduce the noise so that you can see the signal clearly. Okay, so that is the first classical procedure that we see in time series data. So as mentioned, right, it doesn't really involve any model, no model at all. Right, it's just a procedure that you use to trying to see the data pattern in a more clear manner. Okay, so the second procedure that we are going to talk about is what we call the time series decomposition. Okay, so the idea is pretty simple. We talk about this decomposition. You're trying to what? Look at the component, trying to decompose the data into several components. So in the most classical time series data analysis, right? We know that most of the time our intention is to do forecasting. Okay, right. Remember when we do data analysis, our intention is pretty simple. Either we want to do forecasting or we want to learn about the behavior itself, which is trying to explain. You try to explain the behaviors of the data, explain the phenomena. Right. So in this case, you see that in the early days, right, time series analysis is more on this one. Basically, we are not trying to do any modeling to understand the real situation or the real world or how the world behave. But instead, for time series data analysis user, you more give priority to forecasting. So therefore, when you're trying to look at any time series data, let's say we have a Y variable. Okay, so you see a subscript T here means what? Every time period, the value of Y is different, right? So when you look at this time series data, I'm not interested to look at why they behave so. Why it shows an up and down pattern. But rather my intention is to look at what will be the next period's behaviors. Okay, so. look at this, right? So for a simple data like this, all right, so it is generally believed that this simple data can be decomposed to 4 different type of component. Okay, so in this case, any data, any time series data, it can be showing you this 4 pattern, or either 1, or either 2, either 3, right? But these are the 4 most commonly observed pattern in the time series data, right? So the first one is what we call a trend component, right? Trend component is the most common one. So you have the seasonal component, you have the cyclical component, you have the irregular component. So any time series data, surely they will consist at least one common pattern here, right? So, and these are 4 common pattern that you normally see. Okay, so let's try to look at these 4 pattern. Right, try to differentiate between these 4, and we try to see whether we can model them or not. Okay, so visually, what you can see is that, right, if we look at the data, generally these are the 4 common patterns that you see, right? So the most obvious one is what we call the trend pattern first, right? Trend, as mentioned, it can be upward trending, it can be downward trending, it can be linear trending, it can be non-linear trending, right? But how do you define trend here? It's pretty simple, because when you look at this trend must be a long run pattern. Okay, so long run persistent movement. Okay, so yeah, long run. Yeah, persistent movement. So you see, okay, right. And this followed by other type, like for example, seasonal pattern, cyclical pattern, and irregular pattern. So let's look at this pattern accordingly. You see that when we talk about this trend pattern, it is a long run concept. So normally you see this kind of data in a long-term manner. So normally you see annual data, they normally will portray this kind of pattern. Okay, right. So this is a typical pattern that you see. All right. So as I mentioned, this will be a persistent movement, right? So basically, if you show you a long run increase or decrease pattern over time, right? So this is what you see. Right, so it can also be linear or non-linear lah. Just now we look at the annual sales just now, daily sales. Probably it show you a non-linear pattern. Right, now the other one is what we also tend to observe in practice, which is what we call a seasonal component or seasonal pattern. So try to differentiate between this seasonal pattern and long-term pattern, right? Seasonal pattern is a repeating pattern, okay? It is a short-run repeating pattern. What do you mean by short-run or short-term repeating pattern? So this repeating pattern, you will observe within a year. So 1 year, every year, this pattern will keep on repeating. Okay, so what kind of seasonal pattern that you see? So normally when you have high frequency data, high frequency data means what? Monthly data, quarterly data. High frequency means what? How many times you observe the data point in 1 year. Definitely must be more than 1. Annual data is what? It's a low frequency data, right? So 1 year you can observe 1 time. Okay, high frequency data, for example, monthly data. 1 year you observe how many times? 12 times, right? So quarterly data, how many times you observe? 1 year you observe 4 times. So seasonal pattern normally exists in high frequency data, for example, monthly data or quarterly data, Okay, so every year, it will show you a repeating pattern. So for example, we look at this quarterly data. So what is the repeating pattern here? So down, up, down, up, down. So 1 year you see this down, up, down, up, down. So what happened next? Right, down, up, down, up, down. So this pattern, the magnitude can be different. But you see that the up normally is in winter and summertime. Winter and summertime. The down one is spring and fall. Spring and fall. So its pattern is repeating every year. For sure, you know already. But just you don't know how much is that. Okay, so in the industry, you tend to have try to look at this seasonal components for basically for your planning lah. For example, your stock, right? So we are for in practice this kind of seasonal pattern in Malaysia. For example, you see this seasonal pattern, right? So every Chinese New Year or Raya or Deepavali, so festival period. So this is also falls under what we call a seasonal pattern. Okay, so short-term repeating pattern. So we call this a seasonal component. Okay. All right. So another one which is very similar with seasonal pattern, but there is a difference. Also a repeating pattern, right? Just like seasonal pattern, but this repeating pattern is the duration is more than 1 year. Right? Remember, seasonal is what? Repeating pattern within a year. Okay, but cyclical component also repeating, but the duration is more than 1 year. Okay, so in practice, right, this cyclical component, one good example will be like business cycle. You say the business up and down. Okay, so that will be a repeating pattern. For example, in economics, we tend to believe that, like for example, Malaysia, we also experience a business cycle. How long is the business cycle? Okay, from booming to booming, we consider one cycle. Trough to trough, consider one cycle, right? So in this case, business cycle in Malaysia, it take about 10 to 12 years. Okay, so economists like us, we try to we have this kind of worrying because every 10 years or 12 years you see a financial crisis, right? So it's a down. Okay, so business cycle up and down, so up and down, up and down. It's a repeating pattern, but the duration lasting for more than 1 year. So this is what we call cyclical component. Okay. So sometimes these are cyclical pattern you can observe in the industry. The different industry that may have different cyclical pattern, right? So some industry they are anti-cycle and anti-cyclical component. Okay, so which means the economy is doing well means that the industry will not doing well. So when the economy is doing bad, the industry will be going very well. So you have this kind of anti-cyclical component, but again, it also show you a up and down pattern. Okay, now the last one is what we call irregular variation. Irregular means random, like you can't really predict them. Okay, so like the trend component, you see the clear pattern, you can predict them. You see this seasonal pattern, you can predict them. You see this kind of cyclical movement, most likely you can predict them. But for irregular, basically this is the balance, right? Which is the things that we don't see. We don't know what to expect. We don't know how to. So we call this the irregular variation. Okay, right. So this irregular variation happened because of some random event. All right. So we see these 4 pattern already, right? Ranging from trend, seasonal pattern, cyclical pattern, and irregular pattern. So how do we model these 4 patterns? Okay. So in the 20s, right? The classical decomposition method. Try to look at these 4 patterns, right? And then they try to model them. Okay, so there are 2 type of classical component here. Okay, so one is what we the active component here, the additive component. The other one is what we call multiplicative. So you see the name, right? Additive means what? Add, right? Add up. Multiplicative means what? You multiply. Okay, so you see, this is nothing special, right? This is the 4 components that we observe. You have the trend pattern, you have the seasonal pattern, you have the cyclical pattern, you have the random pattern. So total up, it belongs to a common pattern that you observe in a time series data. Okay, so on the other hand, the multiplicative also same. It's just that the operator used is multiplication. Okay, now how do you differentiate between these 2? Okay, so you can see the key difference between these 2, right? When we total up, which means what? When we total up all these 4 components, each component here, right, they will not influence one of another's because you use this add up. So let's say 1 plus 2 plus 3 plus 4, right? Okay, you just total up the impact of each component here. But when you look at the multiplicative, right, you see that the impact of each component, they will be amplified. Okay, so in this case, this multiplicative decomposition basically will give you this multiplicative effects, right? So each component here, they will influence by each other's. Okay, so if the trend pattern is big, you multiply with a bigger seasonal pattern, right? It will make your Y value even bigger. Okay, so looking at the formula itself, you see that when you use additive decomposition method, what do you believe? You believe that each component here, they stand independent. Right, but if you look at this multiplicative decomposition procedure, you basically believe that each component here, they have this multiplicative effects, right? So each component here, they are not isolated. They cannot be isolated. So which means that they are dependent on each other's. Okay, so if big, the impact will carry over to this one, make the Y even bigger. Okay, so let's try to look at it. Okay, so look at the key difference between these 2. You see that the amplitude or the magnitude of the data. All right, so when you use additive composition, basically when you look at the series virtually, you see that the amplitude or the magnitude or the movement or the fluctuation of the data, it doesn't really change much. Okay, in fact, they are changing in a constant magnitude, right? Which means what, more or less the same every year. The growth rate or the movement is more or less the same as time goes by. Okay, so as mentioned, right, same variability, right? So, and then as mentioned, because it is an additive decomposition, you see that the 4 components, they are independent of each other's. Right. On the other hand, when we look at multiplicative means what? Because each component, they are not independent, they can affect one of another because of the multiplicative effects. So you see that the amplitude or magnitude of the changes will be different. They can be going bigger or going smaller over time. Okay, let's look at this. Right, these are several types of commonly seen pattern. Okay, so let's pick one. So you see this, let's look at this, right? What do you see? You see a clear trend pattern, upward trending pattern. You see the fluctuations. And most importantly, you see this fluctuation, okay? They are getting bigger and bigger over time. Okay, so therefore a multiplicative model will be more relevant to describe this pattern, right? Look at, compare with this one. You have an upward trending pattern, and look at the fluctuation along this trending pattern, right? So the magnitude or the amplitude is more or less the same. So adaptive model will be more appropriate to describe this time series pattern. Also, this is what you visualize. Okay, so as mentioned about the classical time series decomposition method procedure. Okay, so that is the classical way, right? Remember, we believe that for any time series data, there are 4 components ranging from trend, seasonal, cyclical, and irregular. Okay, how do you model them? There are 2 distinct ways. One is to use the additive, one is to use the multiplicative. Okay, so this is classical, right? Later on, as time goes by, all right, you see people start to use regression analysis to model this kind of component. Okay, so how do you use this regression analysis to go about the classical approach? Is that you basically trying to capture it in your data. For example, if you see your sales data showing you a clear trend pattern, you might want to capture this in your regression. So for example, you try to capture the repeating pattern, right, or the persistent movement in the data by putting a trend pattern here in your regression analysis. Okay, so if you see there is a seasonality pattern there, what do? You use dummy variable to capture the seasonality. For example, one quarter, you have quarterly seasonal pattern. So one quarter you have 4 seasons, right? So when it comes to regression, remember in your econometrics, you learn what? Because of dummy variable trap, you have to drop 1, right? So to avoid dummy variable trap, so you 4 quarter, you drop 1 quarter. So just put in your regression analysis. So the intention why you do so is that you hope that your model is at the right-hand side variable. You hope that your model can describe your dependent variable in a more precise manner. So what do you observe in your data? So you try to capture them. Okay, so this is the more modern approach that on top of your classical approach, you use a regression analysis to captures the time series decomposition component into your model. Okay, so this is what we see in the later part, right? When you see regression model become more popular. Okay, so your model can be more complicated in the sense that, not only you put your commonly seen component, you probably would like to look at the leg. Okay, so you have leg 1, leg 2, which means that last year sales will influence this year's sales. Last 2 sales will influence this year's sales. So your model can be very rich. Okay, you can put a lots of things on your right-hand side, more with the intention you try to understand how the Y behave. So nowadays, right, a good model not only can forecast, they also can explain. Okay, so that is why when you use regression model, you basically can tell what can you see. So on your right-hand side is your model, how you see the real world. So you see in the real world how these sales work. So it influenced by last 2 years sales, there will be a seasonal pattern and so on and so forth. Okay. All right, so basically we cover these 2 parts already. Okay, so we cover one of the most commonly used time series model, which is the smoothing procedure and the classical time series decomposition method. And then we try to look at the modern approach by looking at regression analysis to reflect your time series component. Okay, so these are the 2 things that we have covered. Okay, so let's look at the third key focus. So let's look at the assumption, right? So what assumption that we'll be talking about is what we call stochastic process. Okay, so let's look at this. Now, from a theoretical point of view, what does it mean in the theory, right? What is theory in the beautiful world? So in theory, what do we believe? For those theories, they believe that if you have a time series data, right? Time series data is just a random, it's a collection of random variable. What does it mean? Let's say you have a series, Y, for example. Y, for example. So this is the time series data. What is the characteristic of time series data? Each observation must be ordered in time sequence. So period 1 come first, period 2 come later, period 3 come later on. So it is a sequential observation. Remember, observation means what? Data point. So for every data point, right, they are in time order. So year 1 must come first, year 2 later on. You cannot put year 2 first. Okay, so what is time series data? From a theoretical point of view, time series data is just a random collections of random variable. Means what? This data point, let's say this is GDP, year 1. This data point can take any value. Okay, when we say this sentence, can take any value means what? Random. Can be anything. What is the GDP for next period? It can be any number, bigger, smaller, negative value, higher, lower, no change. Okay, so each data point, this how you get this data point is it is subject to probability. Means what? It can take any value. Right, so each data point is a random variable. So random point, random point, random point. So you look at this bell shape, right? Remember, you look at this in QD2, right? Bell shape means the probability. So you see, this is the probability that you observe the data point at this value, this amount. Okay, so this is the probability that you observe, right? This value. Okay, so each data point is subject to probability. Okay, so we say that from a theoretical point of view, each data point is a random collection of random variable. Okay, so therefore we assume that each observation value 1 another is drawn from a probability distribution. Means what? The whole process here is a stochastic process, right? From period 1 to period n in futures. The whole process, why do you see this series? Right? So this is what we call a stochastic process. Yeah, the stochastic process. And each data point, they are subject to probability. So how it will move, you don't know one, because it is a random process. Okay, so what is this stochastic process? It's just a collection of random variable. Order in time. So this is random variable, random variable, random variable. So every period you have a random variable. So a collection. So you link this line is a stochastic process. Right. So this is how the theoretical view, right? Look at this time series data. Every data point is a random variable. And when you see this data point over time, so this will become a stochastic process. Okay. Okay, so now look at this. So this is nothing much. This is the theoretical world. So we hate theory because what? It is very abstract, right? Okay, but theories is a cumulative knowledge. So this is what you see. What is this stochastic process? Very simple. Random variable, a collections of random variable. over time. Okay, so random means what? Can take any value. Okay, so this process, which means this line, this process is what we call a stochastic process in theory. Okay, so when you use time series data, right, we are very concerned about how this line behave, how this data observation behave. So what we want is that at best, okay, if can, we want this random process to be a stationary process. So what does it mean? So we want our stochastic process behave in this manner. So compare left and right panel. What is the key difference? So you want what? Each data point. You look at the probability. Is it the same? Yes. So you want that every data point, the probability for each data point to take this value will be more or less the same for the next period. You see? The shape doesn't change, right? So the probability of the occurrence of the data point, right, must be in a similar fashion. Unlike this one, right? Or this one, bigger chances, smaller chances, bigger chances, smaller chances. You don't want that. You want every period, the probability of this value happen is more or less the same. Okay, this is what I call a stationary process. Okay, can you understand? So this line is what I call a stochastic process. And what we want this line come from a random process, which is stationary. Stationary means what? Referring to this curve lah. So every period more or less the same. Okay? So this is what we call a stationary stochastic process. This is not stationary though, because sometimes big, sometimes small. Okay. Right. So we learn what we want is that we want this stochastic process to be stationary. Okay, so in practice, there are two types of stationary stochastic process. One is what we call strict stationary. The other one is what we call weak stationary. So let's try to look at the key difference between these two. Okay, now the first one is what we call strict stationary. All right, so we say this stochastic process is a strict stationary if what? Its properties are unaffected by a change of time origin. Okay, see, property here means what? Property means characteristics. The characteristics of the data are not affected by what? Change of time origin. Time origin means what? Starting point. So let's say you collect inflation data starting from 70 until now. You analyze this inflation. And then I also trying to model this inflation, right? But my data point, I start from 80s. Our friends start from 90s, right? So which means what? Our time origin is different. So you start from 70, I start from 80, our friends start from 90s, right? So if the data is strict stationary, right? No matter you start from 80s, I start from 80s, you start from 70s, our friends start from 90s, the data set will tell us a similar pattern or similar characteristics. It won't change. It will not change if we change our starting point. So if the data gives you this kind of pattern, we say that the data is strict stationary. But what happened is that what? Right? Ideally, we want the data to be strict stationary. But in practice, what do you see? You start from 70, I start from 80. You see different pattern. our conclusion is different. This is what we call not the strict stationary process. So ideally, we want what? Regardless what is your starting point, the data should tell you a consistent story. So that is what we want, a strict stationary process. So why you want this assumption to be there is that you want that when you do analysis, regardless what is your starting point, the data should tell us the same story, right? If your data is not strict stationary, very dangerous. You start from 70, I start from 80s, the data tell us different story. This is something that we don't want. So this is why we pay attention to this assumption. Why do we need to ensure that this assumption hold? Because we don't want that later on, different sample period give us different story. So that is the thing, strict stationary. Okay, so the other one is what we call weak stationary. All right, so compare between strict and weak, right? So what is the key difference? Weak stationary is what I call white sand stationary, covariant stationary, second order stationary. So different type of name, right? But really referring to the same thing. Okay, so what is this weak stationary? So compared to strict stationary, from theory point of view, we'll know that very simple. Our understanding is what strict stationary imply what? The characteristics of the series will not affected by the time origin. As simple as that. Now, from statistical point of view, this is what it means. The joint probability, right, of the data. Look at this. Period data point 1, data point 2, data point 3. So if you have a series of data, year 1, year 2, year 3, year 4, the probability, joint probability means what? I have the joint probability of 2 data set. This is what, let's say 5 years later, right? 5 years later, 5 years later, 5 years later. So these two joined together, the characteristics will not change, right? So I see 3 years later, 4 years later, so the joint probability will remain the same. Okay, this is what we look at the statistical point of view, right? So it's very abstract, right? So when we say very abstract means what? Can you measure this or not? You can't. So in practice, strict stationary process remain as a beautiful concept because we can't verify this. Is our data strictly stationary? We don't know because there's no tool for us to measure or trying to verify it. So strict stationary is a very beautiful concept, but we cannot verify it. So this is the reason why we need to look at a weak stationary. Okay, so we tolerant now, we lower down our expectation, very difficult to work with. So let's look at weak stationary. So if we cannot ensure that our data is strict stationary, what we can do is that we can bound to this and try to look at a lower version called weak stationary process. So weak stationary process, they have these characteristics. Remember, property means characteristics, right? So for a weak stationary data, it must fulfill these 3 characteristics, right? So first one, how do you read these things? Right now, you have to learn how to use notation to communicate your idea. So the E here means expected value. So you expect the value of Y is equal to mu. Mu is the average. It's the long run average. So what is the value of Y? If I ask you, what is the value of Y? How do you answer this? You look at the mean value. So let's say the mean value is 5. So this is the long run mean value. So this is the expected value. Okay, so this value, you see this mu, you don't see any sub t here, no t. What does it mean? It means that regardless what is the time period, the average value will be the same. Okay, this is how do we read this? constant mean value. Constant mean value means what? Here no t. If you have a subscript t here, you see this. What is the difference between this? This is constant mean. So t equal 1, 2, 3, 4, right? Until t. So year 1, year 2, year 3, year 4, all the value is the same. Let's say mu equal to 5. This one means what? The mean value difference for every t. Here means period. So year 1 different, year 2 different, year 3 different. So for a weak stationary, you should have this, the first one, this one. This is violation of the assumption when you see that the mean value is different over time. So the mean value must be the same over time. So let's say, for example, the mean value is equal to 0. See here, which means what? The data point will linger around this 0 value. It will not go far away from this 0 value. Sometimes higher a bit, sometimes lower a bit, but it will not run far away. Right, so wandering around this long run mean value. So this is what I call the long run mean value. So for a stationary process, this is the first characteristic you see. Right. Over time, the series data point will not move far away from this long run mean value. Okay. Now the second one is what I call a variance. The variance. You look at the mean, you look at the variance, look at the behavior of variance data. So how? So how do you measure variance? So same thing, no? Expected value of y, how far y deviate from the mean value, you square it. How far y deviate from the mean value, you square it, is equal to sigma square, right? Again, you don't see these things. Variance is the same over time. Variance is the same over time. Okay, so this magnitude here stay within a constant bound. Okay, this is what we call constant mean value. Right, covariance, the difference between variance and variance. Covariance means what? This is variance. Co means what? Co-author, co-worker, all right? So co means together. So the variance of two data points, for example, the data on 90s, right? So let's say I want to look at the covariance between what? Between data now and 5 years later. K is 5 years, let's say. So my starting point, let's say, is 1990s. After 5 years is 1995 past 5 years later. Okay, so how do I calculate the variance? The variance will be what? So how much your y deviate from the mean value? How much your 5-year data deviate from the mean value? So this is what I call covariance. Variance means what? Variance means like this. You multiplied by yourself 2 times. Covariance means what? You and 5 years later. So this is the covariance of 5-year time. J is equal to 5. Okay, so for every covariance, right? So 5 years time. So the covariance between this value, right, and 5 years later, let's say it's equal to a number, a constant number, let's say is 8. So I change this to 2000, 2005, 2005 to 2010. So the value must be more or less also 8. This is what we mean. Constant means constant variance, constant covariance. So for a typical weak stationary process, the data, okay, it must show you this pattern. Constant means constant variance, constant covariance. Okay, so that is what we call the time series property. Remain the same. Okay, so this is a more concrete way to look at this stochastic process compared to this strict stationary. Strict stationary very weak, right? You don't know how to quantify them because we talk about the joint probability. How do you measure joint probability? It's very difficult to measure. But when you look at the weak stationary, it is much more making sense in the sense that we can study their behaviors by looking at these 3 measurements. So for any time weakly stationary time series data, you will see that the mean is constant, the variance is also constant, the covariance also constant. So this is the characteristics that we want to see. Constant means constant covariance, constant correlation. If a time series data show you these 3 characteristics, then we can claim that this time series data, they are weakly stationary. So if a violation of this means what? Violation of this says what? Non-constant variance, non-constant mean, non-constant covariance means what? It is not a weakly stationary process. Okay, so that is basically concept. Okay, so for a typical weakly stationary data, this is the characteristic. If you plot it visually, we got without the hassle of going through this calculation, visually you probably can see this kind of pattern. So if you roughly you see that the data show you a mean reverting pattern. Mean reverting means what? Coming back to the mean value. No matter how far you go, you still coming back to the mean value. This is what I call a mean reverting characteristics. So for a weakly stationary process data, they will show you this mean reverting pattern. Right? Constant variance means what? The fluctuation will not go far away from this constant bound. Okay, sometimes big, sometimes small, but it will not go far here, the fluctuation. Okay, of course, if you see this constant bound, most likely the constant covariance will be whole as well. Okay. So in this case, we learn 2 concepts. So what we want for any time series data, we want to look at their stochastic process. And we want this stochastic process to be stationary. So, stochastic process. And we want it to be stationary. And for stationary, there are 2. One is what we call strict, and one is called the weak. So strict stationary means the joint property must be the same. Right, weak stationary means what? Mean, variance, covariance must be constant. So this is what we learn. Right. So in practice, although we want that our data to be strict stationary, but we know that it's very difficult for us to quantify. Okay, so what we can do in practice is that rather than looking at the strict stationary, we pay attention to the weak stationary. So when you look at time series data analysis, right? Time series analysis, when I talk about stationary means what? Normally we're referring to the weak stationary, not the weak one. Okay, right. However, okay, because right, if you look at the time series data, if you see that your data is weak stationary, right? and you further try to look at the behaviors of your time series data and check whether they are normally distributed or not. So a weak stationary data plus a normal distributed data, these two together is equivalent to strict stationary. So no way we can measure strict stationary, but we can measure strict stationary in a indirect pattern. Also, if your data is weak stationary and your data is normally distributed, so coupled with these two characteristics, right, it implies that your data is strictly stationary. Okay, so that is what we see. Right. So from this, you can see, is this a stationary series? Yes. Fluctuation linger around this constant mean value. How much is the mean value? Roughly is 0. Fluctuate within a constant bound. So this is a typical stationary series that you see. Look at this. Is this data stationary? Do you see constant means, constant variance, constant form variance? No, you don't see that. So first you look at what? You see whether do you see mean reverting pattern or not? You don't see this, right? So looking at the sample data, the mean is not reverting. In fact, the mean is increasing. Increasing mean value over time. Every period, every sub-period, the mean value is different. All right. How about the variances, the fluctuation? So this period, the fluctuation is bigger. This period, the fluctuation is smaller. So the variance is different. Okay, so we say that the variance is time dependent. It depends how much is the variance. It depends on where is the sample period you're talking about. Right, so you see the variance is time dependent. Now the other one, what you see is that you see there is a persistency. What do you mean by persistencies? Persistent means what? It is a characteristics where your data is influenced by its past value. Okay, persistent. So your behavior now is highly influenced by your past behaviors. This is what we mean persistent in time series data. And this is a very common pattern that you see for time series data. So why you see this persistency? Very simple, because we are talking about human behaviors. Human will not suddenly change. Right? If today you are hardworking, means what? Yesterday you also hardworking. Next day you will be hardworking. You will not suddenly become lazy, am I right? Unless there are certain external events. Today you are lazy. Tomorrow sure lazy lah. Where got suddenly hardworking one? Unless the exam is coming, am I right? So we call this kind of characteristics is what we call the persistency in the data. So because of this persistency nature, you see that data tend to be showing you a trending pattern. So which means what? Let's say, for example, here. This is the amount of data that you see, right? So what will be the next period? So your behavior in the next period is also influenced by your last period. Also, your behavior in the past will carry over to the next period. Your data will carry over effect. So it will make your value of the data become bigger and bigger every year. Okay, so previous effect plus now effect. So you see this value is now. How much is the Y value? The actual value now plus the previous effect value. So total up together, you get this period value. Right? So this previous effect, this value will keep on adding up, the cumulative effect. So this is the one that making your series behave in a trending manner. And in statistical, we call this as persistency in the data. Or some data are very persistent, means what? Highly correlated with the past. Some data is less persistent, means what? Not so much influenced by the past. This is like human being lah. Some people haunted by their past, some people no. Okay, so see whether the data is highly persistent or less persistent. But if you see there is a trending pattern in the data, this most likely suggests to you that the data is persistent. Okay, so can you see the clear difference between these two? This is a typical stationary data, mean reverting, constant variance. So this is typical what we call constant variance, constant covariance, constant mean. But a non-stationary data violate everything. You see what? Non-constant variance, non-constant means, non-constant covariance, that is show this kind of characteristics. So visually, right, you can roughly guess whether your data is a weakly stationary data or is a not stationary data. If you see this not stationary, we worry. We don't want this. What we want is this one. We want our time series data behave in a stationary manner. So if your data behave in this way, means what? I analyze sample 1, you analyze sample 2, the result will not run far away. But if my series is non-stationary, you analyze period 1, I analyze period 2, you might get different result. Okay, so that is the rationale. Why do we want stochastic process to be a stationary process? Okay. Different terminologies used to describe non-stationary series. So even though we look at stationary versus non-stationary, right? So in practice, many people use different name lah. Some people use random walk. When your data is non-stationary, they call this a random walk data, a non-stationary data, a stochastic trend process, stochastic trend data, right? The I1 data, integrated and order 1, unit data. So these are different name used. We talk about this, just a name. Okay, so we have covered until this stochastic process. Can take it or not? So it's a theory concept, But I hope that at least you know why we want this concept to be there. Okay, right. Next one. We want to look at the trend in time series data. Right, remember just now when you say, the data must be stationary, okay? And in practice, normally we see that the data normally are non-stationary because there is some persistency in the data, okay? Persistency of the data will reflect in your graphical plot lah. Or any data that show you trend pattern, most likely they are non-stationary. So let's look at this trend pattern or persistency in the data. Okay, now first, I want to share with you this quote by Professor Peter Phillips. Phillips is the one that introduced a test how to examine whether our data is stationary or non-stationary. Okay, so Professor Phillips highlighted that no one understands trend, but everyone sees them in the data. Okay, so this referring to time series data. When you plot your data, most of the time you see that your data will behave in a trending pattern. So why you see that? Just now we say it's because of persistency in the data. So why do we have this kind of persistency? Also, this is things that we trigger our intention to study this. Also, in session 4, we want to look at this trend pattern. Okay, so trend in time series data are why. So wanted to know why do we see these things, right? So trend, by simple understanding, trend is just a long-term upward or downward movement, persistent upward or downward. Okay, so persistent means what? Influenced by the past value lah. So if last year value high, this year will be higher lah, right? So this is what it means upward trending is if last year period is low, next year will be higher a bit. So you see this kind of things, right? So what are the factors affect the trend is because, so trend pattern is the unobserved pattern. Unobserved phenomena. It tries to measure unobserved phenomena. For example, when you look at the GDP is going up every year, higher and higher. Okay, why the GDP value is higher and higher? Because the GDP value reflect cumulative effects from the past. What kind of cumulative effects? And this cumulative effects, most of the time we not able to observe it. For example, that the whole society experiencing technological growth. Okay, so the technological growth here, for example. Okay, so it makes the society become better and better. Okay, let's say for example, medical advancement, right? They make the society become better and better over time. So you see this trend pattern. Okay, so change in the consumer taste. Suddenly you see it reflect the value become increasing over time. Suddenly the change of the society change already, the pattern of the society change already. For example, nowadays people are more inclined to vegetarian, for example. Okay, so you see that the trending pattern change. Market growth, for example, you have the new industry coming in, it reflects this kind of unobserved pattern, right? Or inflation or deflation that make your GDP go up or go down. So these are the unobserved things that make the series move in a unanimous way. Okay, so two types of trends seen in time series data. So we see that it's a persistent upward or downward movement, right? How do we model this kind of movement? So in time series analysis, there are two ways. One is what we call the deterministic trend pattern. The other one is what I call stochastic trend. Okay, let's look at the key difference between these two. So how do you model trend? You see data is going up or going down in a persistent manner. So how do you model them? So these are two common ways. As the name suggests, right? Look at the name you see. Deterministic means what? You can determine the changes. Stochastic means what? Random. Random means what? Unpredictable. Okay, looking at the name, basically you can guess the key difference between these two. So deterministic trend, how do you model them is using a regression model. All right. Now, this is your variable y. Y can be anything, can be sales, can be GDP, can be inflation. So on your right-hand side, what do you see? You see this is what I call a linear trend. Okay, linear trend means what? Year 1, your trend take value 1. Year 2, trend take value 2. Year 3, take value 3. 1, 2, 3, 4, 5 until, let's say you have 30 years, so you have 1 until 30. It's a linear trend pattern. If you suspect that the series moving in a linear trend pattern way, you put a linear trend on your right-hand side. So what do you see? You see that the movement in the data will captured by this alpha 1. Alpha 1 equal, alpha 1 equal to change in Y due to change in the trend pattern. What is trend? equal to 1, 2, 3 until, depend on how many sample data you have, 30. Okay, so let's say I'm getting this value, y2 plus 3 trend. So what does it mean? It means change in y due to change in trend is equal to 3 over 1. So how much y will change if your trend pattern is changing? So for every 1 unit, you expect what? It change 3. So if this, let's say this is y is what? Billion, RM billion. So for every year, it changed about what? 3 billion ringgit, for example. So how much you expect? So if I see my data like this, y, okay, it's a linear trend pattern, right? So what do I expect? This data y, every year it changed about 3 million ringgit. Oh, so can you predict this? Yes, because you see that the changes is captured by this alpha 1 value. So it's predictable in the sense that we know how much it will change. So how about next year? How about next 2 years? How about next 3 years? You know that the value will not change. It's about 3 billion, for example. Okay, and of course we want that the alpha is lesser than 1, so we want it to be lesser than 1 means what? What is this? Alpha 1 is lesser than 1. I don't think this is right. This one is I take away the sorry. Remove. Okay. Right. How about the stochastic trend? Stochastic trend is pretty simple. Stochastic trend means what? You cannot predict how much the value will change over time. All right. So it is hardly predictable because the variation is systematic. Okay. So what does it mean? So like this case. All right. So look at this value. What is the coefficient here? It's 1, right? This one is silent, right? You will see a coefficient for this value, but because this is 1, so you don't see any symbol here. So what does it mean? So if I see this alpha 2, what does it mean? Change in y due to change in yt minus 1, right? So if this is equal to 1, what does it mean? It means that the data is a stochastic trend data. Which means what? What happened in the past? Last year, what happened? 1 unit change in last year will 100% carry over to this year. So when this value is equal to 1, right, you see that the relationship between y and yt minus 1, it is 1-to-1 relationship. This is what we call a stochastic trend pattern, whereby what happened in the past will fully reflected in the next period. So how much is this year value? We don't know because there is a random component here. You don't know how much is this. And this one, the effect is 100%. Last year effects 100% affect this year plus a random component. So you don't know how much the y will change this period. Okay, because the coefficient for the last year take 1 value. So this is a typical non-stationary process or stochastic trend pattern that we see. So these are 2 common way to model the trend pattern. One is through using a linear trend, and we call this a deterministic trend. The other one is try use C and set the coefficient equal to 1. Okay, if this value is equal to 1, then the series is non-stationary or the series contains stochastic trend pattern. As I mentioned, non-stationary means you don't know what to expect. It will far away from the long run mean value, so it's basically non-predicted value of y. Okay. Okay, so if you have this kind of trending data, what should you do? So again, trend pattern indicate that the data is non-stationary. When the data is not stationary, using non-stationary data is very dangerous because different subsample will tell you different story. So in practice, what do you do when you see your data is trending, right? What do? You have to remove the trend. So trend is just like cancer. You have to remove the cancer from your data. So how do you remove it? Depending on how you model it. So if your data is deterministic trend, how do you remove it? You detrend it. So this is your deterministic trend model. Let's say this is 2 plus 3. So what you do is that you move to the left-hand side, right? Minus it out. Left your deterministic component. So this is what we call the trended series. So if your data is deterministic trend, remove the trend by detrending it. Okay. So if your data is stochastic trend, remove the trend by differencing it. Remember this differencing that when we talk about it in the first key focus, differencing your data. So differencing is one way to remove the stochastic trend in your data set. Okay. So in practice, most of the time you see that our data can be deterministic trend or can be containing stochastic trend. So in practice, most of the data is stochastic trend pattern. Right, deterministic trend is very seldom we see data with pure deterministic pattern. In practice, mostly is stochastic trend or deterministic trend plus stochastic trend. Seldom we see a pure deterministic trend data. So that is what you see. Right, so we have covered all these things. Okay, let us look at the last part on spurious regression problem. Okay, so what is this spurious regression problem? Simple. Spurious regression problem is an econometric problem. So we say, whenever you talk about econometric problem means what? It must violate certain assumption. Econometric problem always referring to violation of assumption. So when one of the assumption in time series data, which is what I call stationarity, is being violated, then it will give rise to spurious regression problem. Okay, so what is this spurious regression problem? All right, simple. Okay, so spurious regression problem happen when what? Okay, when you use non-stationary data. Okay, let's say for example, I do regress time 2 times series data. So variable y, variable x, and y and x theory say what? Theory say it should be stationary like this. Constant means constant variance, constant covariance. Theory say, at best must be like this. But unfortunately, in practice, we don't see these things. Violation of assumption, normally you give rise. So your y is non-stationary, your x is non-stationary. When you try to regress these things, regress a non-stationary series on another non-stationary series, if you give rise to what we call spurious regression problem. So what is spurious regression problem? Spurious regression problem say, okay, the statistical result is very beautiful, but you cannot trust it. Okay. In other words, it says what? The statistical analysis will tell you there is a significant relationship between X and Y, but in practice, there's no relationship at all. So this is why I call it as a spurious regression problem. Spurious means what? Fake. These two variables, there are no relationship one. But because you see they are non-stationary, whenever you regress them together, the statistical tools pick up the trending pattern. So OLS think that, oh, this is going upward. This one also going upward. Most likely these two are significantly related. So what the regression pick up is the statistical movement. It's not the general relationship between these two. And the statistical T will tell you that, oh, it is highly significant in this case. Okay, so that is what we call a spurious regression problem. Spurious regression problem is a fake regression. So it means what? The statistical result will tell you a very beautiful result, but you cannot trust them because what they pick up is just a common pattern in the data set. Okay, so how do you know there is a spurious regression problem? We don't have any test for you to directly test it, right? But as a rule of thumb, you can roughly use this rule of thumb to check it. One easy way is to look at the R-square and the Dublin-Watson statistic. Okay, so there is two conditions. So if you regress, you check the R-square, you check the Dublin-Watson statistic. So Dublin-Watson statistic range between what? 0 and 4. In the middle, you are 2. So this is very hot, this is very cold. So in the middle, you are all right. So Dublin-Watson is a test to detect autocorrelation problem. So if your Dublin-Watson close to 2, you are all right. If you're close to 0 and close to 4, you will have autocorrelation problem. Okay, so now you compare with R-square, and you know R-square must range between 0 and 1, cannot be more than that. So if your R-square is greater than your Dublin-Watson, you start to suspect that the regression basically suffer from spurious regression problem because a small lesser than 1 Dublin-Watson indicate that there is an autocorrelation problem. Okay, so but when you run the regression in first different, means what? You change this to first different form. And then your R-square will be close to 0. Your Dublin-Watson is close to 2. So which means what? What do? You're removing the trend. So this is trending series. Data content cancel. When you regress this, your body will tell you different story. It tell you that, oh, there is a significant relationship between these two. Can you trust them? You can't trust what they pick up. It's just a trending pattern there. Okay, but once you're trying to cure the cancer, you try to remove the cancer from your data, the data will tell you, or statistical test will tell you a genuine result. Or means that X and Y, they not belong together. You see that R-square is close to 0. Okay, and there's no autocorrelation problem. Remember this R-square, what does it tell you? R-square tell you how well your model explain Y. Closer to 1 means what? Very well. R-square is just like your test score. How well you perform. How well your model explain Y. Okay. Close to 0 means what? The model doesn't explain the Y. What model is this? The model referring to your right-hand side variable. What right-hand side variable you are looking at? X variable. So X doesn't, the change in X doesn't really explain much on change in Y, which is making sense, right? So in this case, this is what we call spurious regression problem. And these are the indirect way for you to check this spurious regression problem. Okay, right. Let me show you one classical example. How do you look at this spurious regression problem? Okay, so this is one very classical example used by Professor Henry in one of the paper published in the old days when they start looking at this time series analysis, where the spurious regression problem arising become a critical issues. So Professor Henry show you one example. It says, okay, now we want to look at what explain inflation. So you want to build a model. Pay attention to the inflation. So how your inflation is a function of axis. So we want to build a model that can explain the inflation in UK. So how to go about this? Very simple. So you look at the data. So he used the P. P is the inflation, consumer expenditure as deflator. He used deflator as the proxy for inflation. And then he looked at a variable C. So he believed that inflation is determined by a C factor. Later on, we see what is this C, yeah? So you have your model already. This is the model. Then you look at the time plot. This is what I call a time plot. Time plot means what? Data over versus time. So what do you see? You see this inflation P. Price is increasing over time. C variable also increasing over time, but this one is a linear increment. This one is the non-increment. So to better capture this, he saying that, okay, I need to bring in the non-linearities. So C square, because it's like this curvy form, right? So go down and go up later on. So what do you see? You have to bring in the non-linear. So this is non-linear. Right, inflation is non-linear, and then you have the linear variable. So you want to capture the non-linearities. So this is to capture the non-linearities. So his model basically is like this. So what do you expect? Non-linear, ma. So go down first and then go up. Go down means what? Negative, and then go up. So you expect this value, the beta value here, take negative. This value take positive value. So this is his model. You see that it seems that it suspect that C is the one that contribute to inflation in UK. So looking at this regression, look at his result. Do you see? What do you see? This is the result. And this is the standard deviation and standard error. So standard error measure what? Standard error measures how precise is your estimate. The smaller, the better. Because when we perform hypothesis testing, you need this standard error. For example, I want to look at the C. C, is it negative? It is negative. This one, is it positive? Yes, it's positive. So there is a non-linear relationship coming in. So let's say I have negative 3.2 divided by 0.23. So how big is this? Yeah, this one, 3.2. 3.2 divided by 0.23, I get 13.91, right? So it's a negative. So this value is a big value, right? Because looking at the t-test, the critical value, 1%, 5%, 10%, right? How much is this? 1.645, 1.96, 2.58, right? So this number is greater than 1%. So it's a highly significant result. Same things with this one, positive 0.39 divided by 0.02. What do you get? Let's see. 0.39 divided by 0.02. 0.39 divided by 0.2, you get 19.5, right? It's also highly significant result, right? So reject at 1%. Okay, so you see the 8 variable C seems to be a very significant value. Significant means what? Important, huh? Highly significant result to explain your price. And you look at this R square. Right. Remember this value almost hit 100%, right? So you convert to percentage form, right? So it becomes 0% into 100%. How well your model explain? 98.2%. So is this a good model? Yes, it is a good model. So C and C squared is a good model to explain your P. Okay, unfortunately, the W Watson is quite low, right? Right. So now, looking at this, at first, right, you look at the surface, it seems like the C is a highly significant variable to explain your inflation. Okay, but what is C? What explains C? C is what? Cumulative rainfalls in UK. So you look at a beautiful model like this, look at logical point of view, right? Does it make sense or not? The more rain you have, the more inflation you will experience. Makes sense or not? It doesn't make sense, right? But the t-test tell you otherwise, tell you that, oh, this is a very beautiful model, right? The variable are highly significant, okay? So R square is very high. So you look at the result, you tend to believe that C is an important factor. But does it make sense or not in a logical manner? So it's not making sense. This is what we call the danger of doing spurious regression problem. Why this problem happened? Because there is a trending pattern in your P, there is a trending pattern in your C. When you're trying to regress model with the trending pattern C and P, you will tend to get this result. High R square, but the W Watson suggests to you otherwise because W Watson value is quite low, suggesting that there is autocorrelation problem. Remember in your econometric, when there is an autocorrelation problem, what is the consequence? Right, consequence is that your hypothesis testing can be misleading. You can't trust them. Okay, so this is what you see. All right, when the series is trending, when the series is trending, the regression will tell you a very misleading result. So that is what we call spurious regression problem. Okay, so I guess this concludes the material for topic 1. Right. We will try to go through one example on spurious regression problem so that you can comprehend more. Right. So let's conclude on topic 1. This is some basic concept that you need to know. Okay, any question so far? Okay, any question? Can understand? So I will prepare some question for you to practice for during our tutorial. Tutorial will start in week 4. So after you come back, I don't want to have a e-class for tutorial, so we meet physically. So tutorial class start in week 4. Okay. Right. So any question from your side? Any questions that you want to ask? Stop recording.